to record as well. So I'll hit that record button. We have a post-course survey that's due tonight. So if you haven't taken that yet, remember the two together, the pre-class survey and the post-course survey make like a total of 1%. So that's kind of like the roundup. So if you're quite close to the next grade point, right, you really want to make sure that you've done those, just that way you have kind of every point possible. And so there's a link available in D2L. Again, that's due tonight. So make sure that you take it before midnight. Today we're going to be covering chapters 11, 10, and 8, right? Last time we covered chapters 5 through 7. And then finally on Friday, even though there is no class formally, right, I am holding a review session. So from 4 until 5 o'clock. So that's my normal office hours. I thought that would be maybe time better spent doing a review session. Everyone's welcome to join that. And just to make sure that we have a decent distribution of questions, and I can think about kind of what I want to say beforehand and all that sort of stuff, please, if you have a question that you want to ask, it's best if you let me know what it's going to be through this form. I've had review sessions where the very first person, you know, if I'm just taking free form questions, the very first person asks a very difficult question, you know, maybe a challenging question that they found online or the textbook or, you know, even the challenging questions in web work, and it takes me 40 minutes to explain it. And then essentially the entire review session is, you know, shot doing that sort of deal. So it's better, I think, to have more questions that are, you know, more, you know, at the exam level difficulty, something that's actually intended to be done in 5 minutes or so, rather than a very difficult question that's intended to be done over, you know, a half an hour or an hour. Sort of deal. So yeah, if you would please let me know what questions you're interested in covering, and that's what we'll be talking about on Friday's class. For today's class, again, there is a link here. Yeah, I see in chat here, will the Friday review session be recorded? That just popped up. And yes, I will plan on recording that, and I'll just post it probably under the D2L announcements. I may also try to find a space for it in the navigator and all that sort of stuff. So maybe I'll sprinkle it around a few places, maybe also Piazza and whatnot. But yeah, I'll plan on recording that and posting it for anyone who wants to. Of course, that's not worth attendance points or anything like that. That's just some bonus information, I suppose. No class on Monday, and it's going to be the class link here. So it's the class link, because in my dreams anyway, we have quite a few people. So I want to make sure that we're not coming up against the Zoom limit or whatnot for how many folks. Oh, my cat sees a bird. She may end up having to go sit closer in the window. We'll see. But yeah, so I plan on using this link right here, the link that you came to for the Math 133 class, just so that way, in case a lot of people do show up, you know, you're not turned away because of arbitrary Zoom limits that they have. So, okay, with that, please get your votes in if you've had a chance to look through some of these examples, and we'll go over the most popular one here first. I have a question. Will the help room be available Thursday or Friday? I don't know the answer to that. I would probably guess on the MLC website. If they have any closures, usually they put that on the MLC website, just a FYI. So I'd look there. If it doesn't say they're closed, then I would guess that they're open. And that would make sense anyway for the study days. Okay, well, with that, let me look over here really quick and see what responses we have, what you're interested in covering. And it looks like example 13 is kind of way out in front. So we'll take a look at example 13 as our first question. Again, continue to get your votes in, and I'll go ahead and, oh, that's a very close bird, isn't it? Yeah. I'll continue to look at the results, and we'll go over, you know, the second popular question next. So, all right, in this case, we have a function 1 over x. We're interested in the Taylor series generated about the point x equals 3. We're going to use sigma notation to give our final answer, and then we're going to try to determine the open interval of convergence from our series here. So, okay. With the Taylor series, remember, we have on our formula sheet, and by the way, it's a good idea that, right, the formula sheet is already posted on D2L. I would recommend that you print that off and start carrying it around with you now. just so that way you know exactly what's on there and what's not on there. For instance, they give you the formula for the Maclaurin series on there, but they don't give you the formula for the Taylor series. But of course, basically you just change a few zeros to A's, and that will be the Taylor series formula. So you need to know that first of all. Right, we have this whole list of some power series, right? I think that's the header for that category. And so you get some of these things like 1 over 1 minus x and things like that. But remember, when we were talking about this in 11.10, right? This is where we were talking about Taylor and Maclaurin series. Here, why don't you go over to the window? No. She's just scratching up my arm right now. When we were talking about this in 11.10 and everything, we had this wonderful list of some power series, but remember, you don't get to use that whenever your center is not about 0. That's only really good for when you have a Maclaurin series or you have a Taylor series centered about 0. And so because we're centered about x equals 3, yes, thank you. Go ahead. Go ahead. Those don't work. So we need to use the definition. All that to say, right, we need to use the definition on this here. And so the definition, right, goes, we're summing up various derivatives, right, at our center A, divided by n factorial times x minus a raised to the nth power, right? And we start off at our 0th degree, then our 1st degree, then our 2nd degree, and we keep on going forever and ever and ever. And these, right, I usually call these things infinite polynomials, right? And so they just go up, keep on going on forever sort of deal. And so for this, we can quickly say that our center here, right, it's about this point x equals 3. So that right there is another way to say what our center is. So we can go ahead and plug those things in here rather fast. N equals 0 to infinity. The nth derivative at 3 divided by n factorial and x minus 3 raised to the nth power. And again, kind of when we were doing this in class, right, quite often I would also carry around maybe like the first 4 terms, but because it says that we want our final answer in sigma notation, maybe I don't need to do this, right? I can just kind of leave it in this form here. So we pretty much have everything except for, right, this formula right here. We need to know, what does the nth derivative at 3 actually look like? And so in order to figure this out, usually I recommend getting kind of a running start at this. So that is, I'm going to figure out what is our 0th degree or our 0th derivative at 3, aka just f of 3. What is our 1st derivative at 3? What is our 2nd derivative at 3? And let's maybe do a 3rd derivative. That will probably give us enough. That's kind of our running start here to figure out what should the formula look like in general, right? If you have an nth derivative at 3, right, what that exactly looks like. And so f at 3, of course, is quite simple. We just plug in 3 everywhere we see an x into our function. For the derivative and 2nd derivative and all that sort of stuff, well, now we need to actually start taking derivatives. So I'm going to go off to the side here a little bit more and take a derivative. And so remember, this is the same thing as x to the negative 1st power. That's 1 over x. And so when I take the derivative, right, I'm going to have this negative 1 come down. And then I'm going to have x to the negative 2nd power, or that's going to be the same thing as 1 over x squared if you want to simplify. So when I plug in 3 here, I'm going to have now negative 1, and I'm going to have 3 squared on the bottom. Another good hint for you guys for trying to figure out, right, we're going to try to get a formula down here. And so a good hint or a good way to kind of do these things is to resist the urge to simplify at all. Sometimes simplifying actually hides the pattern from us. And so by not simplifying, kind of you can see where all of your numbers are coming from a little bit more easily. So I'd recommend, you'll see that I won't simplify darn near anything, even though I could. All right, next up, let's go ahead and take a 2nd derivative. When I take a 2nd derivative, let's see, well, the negative 1 is going to be along for the ride. And when I take the derivative of this, we're going to have a negative 2 come down, right? Because this is really x to the negative 2nd power. And then I'm going to reduce my power by 1. And so I'm going to have x to the negative 3rd power. That's the same thing as 1 over x cubed. And so here we're going to have negative 1 times negative 2 divided by, and I'm going to plug in a 3 everywhere I see an x. And that's going to give me my 2nd derivative at 3. Let's do this one more time, and then I think we'll be ready for the pattern in general. Taking another derivative, let's see, I'm going to have -1 times -2 times -3, right? Because when I take yet another derivative, the -3 is going to come down, and I'm going to reduce my power by 1 to get me x to the -4th, and I'm going to write that just as the reciprocal here. And so I'm going to have -1, -2, -3, all divided by 3 to the 4th power. And this is what I'm meaning by, right? It'd be very tempted to maybe simplify, right? We have a 3 on top and a 3 on bottom, those cancel, right? But if we cancel those, again, kind of, it's a little bit harder to see the pattern, what's going on here. So now I think we're ready to try to come up with a formula in general. It looks like in our denominator, we always have a bunch of 3s. And the number of 3s that we have, right? First of all, we started off with 1 3, then we have 2 3s, then we have 3 3s, then we have 4 3s, right? As we take more derivatives, we're getting more 3s in the denominator, right? And so this is going to be 3 raised to some power. And maybe if I was going too fast, I would just say it's 3 to the nth power. What is it actually? This isn't actually the formula right there. What should it be? Yeah, we need an n plus 1. Right? It's the number of derivatives plus 1, right? So when I took 0 derivatives back here, right, there was 1 3 in the denominator. When I took 1 derivative, there was 2 3s in the denominator, right? It's always the number of derivatives that you have, but 1 more than that. So it's going to be 3 to the n plus 1 in the denominator here. Now in the numerator, it looks like we're almost getting something that looks factorially, right? For instance, you really start to see the pattern down here, right? 3 times 2 times 1. Here you see the 2 times 1. Here you just see a 1. Here you just see a 1, which, by the way, 0 factorial is 1. And likewise, 1 factorial is 1. 2 factorial, that's the 2 times 1. 3 times 2 times 1, right? So this is really looking like an n factorial. The only problem is if I write down n factorial, it doesn't account for all of the negatives. So I can do this, but then I have to kind of think about my negatives separately, right? For instance, when I took 0 derivatives here, I didn't have any negatives. When I took 1 derivative, I had 1 negative. When I took 2 derivatives, I had 2 negatives. When I had 3 derivatives, I had 3 negatives, right? So it always seems to be there's the number of negatives here, the same number as the number of derivatives that we've taken. So I'm going to write -1 raised to the nth power, and that will account for all of those negatives there. And of course, right, every 2 of them or so, they'll cancel and just make a positive. But this is a good way to represent that. So all of this work, this is really the most difficult bit, is trying to figure out the formula for the nth derivative at 3. Now that we have that, we can go ahead and plug this in. And so this is going to be -1 raised to the n times n factorial divided by 3 to the n plus 1, all divided by n factorial times x minus 3 raised to the nth power. You can see, right, we have fractions over fractions. So instead of dividing here, I'd multiply by a reciprocal. But we can also see that there's going to be an n factorial on top. And then when I multiply by the reciprocal of n factorial, 1 over n factorial, right, that'll cancel there. And so my final answer, everything all done, is going to be -1 to the n divided by 3 to the n plus 1. Those n factorials canceled. And then here's our variable stuff here. So that right there would be my power series centered at 3 for 1 over x. Of course, if this isn't on, during an exam or a timed assessment or whatnot, you can also go to like Desmos and plot these things and see that, yeah, this is lining up very well with 1 over x, especially around x equals 3. Okay, with that, I'll pause for just a quick second before we go into B and just see kind of how you guys are feeling. No raised hands right now. All right.
There's one question one interesting question asking in the Q&A.
Good.
Why can't you use -1 factorial instead of -1 to the n times n factorial?
Yeah, so factorials are only really well defined as we have them right now for positive integers, right? And so if you try to use them, even with like fractions and stuff like this, right, what does it exactly mean to say you know, 3/2 factorial. When would you ever stop, right? According to this, right, you would go 3/2 times 1/2, and then it's not clear, would you stop there? Or would you go -1/2 next, right? Kind of previously it always stopped when you get to 1. And so this doesn't really make a whole lot of sense. And so likewise, if you have negatives here, it's a little bit of a problem. Mathematicians have recreated the factorial function for rational values and negative values and all this sort of stuff. It's the zeta function, right, Yuan? You would know this better than I do.
Sorry, what's that?
What is factorials in general? Isn't it the zeta function?
I'm not sure.
Okay, yeah,
Gamma function or zeta function?
Oh, yeah, I think you're right. I think you're right. I think it is the gamma function. So if you'd like to do some fun searching on Google and Wikipedia and things like this, YouTube, yeah, I think it's the gamma function. You're right. And so this is kind of the generalized version of factorials. Yeah, capital gamma, yeah. Good. So let's also do B here. Find the open interval of convergence from your series from A. And so, okay, well, this one right here, right, if we had done, if we were able to do, we're not even able to do some formula, you know, based on this sum power series, right? Because this wasn't a Maclaurin series, so we can't really use any of that. Then you could use the radius of convergence from those given series. But in this case, right, since we don't have that, we just need to go back to our 11.8 method, and that was ratio test, right? And so we're going to apply the ratio test, the limit as n goes to infinity. We're going to take subsequent terms here, n plus 1 divided by, n plus 1 plus 1, so n plus 2 there. And here we're going to have x minus 3 raised to the n plus first. And we're going to divide that by our a sub n. And so, okay, a sub n. And again, maybe you've done so many of these things that you're already kind of getting to simplifying it and all that sort of stuff. And that's certainly fine. I'm going to combine like terms or kind of put these at least next to each other. We're going to have -1 to the n plus 1 divided by -1. We're going to have, let's see, the 3's on the bottom. Oops, and I missed my plus 1.
Where's the n?
Sorry, what's that?
Negative to the n. -1 to the n.
-1. Oh, to the n. Ah, yeah, thank you. I'm just dropping all sorts of variables here.
Yeah.
I'd like to believe I was going to catch myself. These things, you know, once you've done so many of them, you kind of are thinking already what's going to be happening here, right? So for instance, a lot of -1s are going to be canceling out, and I'll have one more on top than I do on bottom. A lot of 3's are going to be canceling out, and I'm going to have one more on bottom than on top. And then here, a lot of these x minus 3's are going to cancel out, and I have one more on top than I do on bottom. And now notice there are no more n's, right? I've canceled out everything with an n is just gone. And so as n goes to infinity, right? Well, this is constant with respect to n. So I can apply my absolute values. Absolute value of -1 is 1. Absolute value of 1/3 is 1/3. And absolute value of x minus 3 just is what it is. And if you want this to converge according to the ratio test, you need to have this limit less than 1. That's what it says according to the ratio test. If it's greater than 1, it diverges. If it's equal to 1, right, a little bit mysterious, and we have to check those things. And so at this point here, we have now the radius of convergence. The radius of convergence is 3. And if we go ahead and we split this up, right, instead of an absolute value inequality, we write the equivalent compound inequality. Then we can go ahead and rearrange things a little bit, adding 3 to all sides, and we'll see on the interval from 0 to 6. So long as x is in this interval from 0 to 6, this power series will do a good job, right? That's the open interval of convergence. If it asks for just the regular old interval of convergence, we would have to check endpoints, right? But because it asks just for the open interval of convergence, right, it doesn't care about those endpoints. So we're done right now. So yeah, that's my final answer there. Excellent. Looks like there's one raised hand. Let's go ahead and call on Anito. You have the floor.
Just quickly, because you just brought it up, could you explain how you would do the endpoint, thing?
Yeah. So if you would plug in x equals 0, and you would plug in x equals 6, right? And you would see at each one of those x values, does the corresponding series converge or not? And so maybe we could at least look at, let's just do the 0 one. So again, kind of I'm going back to my power series here. And now everywhere I see an x, I'm going to plug in a 0, right? So this is going to give me summing up from n equals 0 and beyond. We're still going to have this -1 to the n. We're going to have 3 to the n plus 1 here. And now instead of x, I'm plugging in 0. So it's going to be 0 minus 3 raised to the nth power. So at this point, well, 0 minus 3, we're just going to have -3 here raised to the nth power. And then you can use properties of exponentials here, right? We could go ahead and combine these things, for instance. And -1 times -3 is going to be 3 to the nth power. Right? Both of these things are being raised to the nth power, so they can multiply together very nicely. And now, well, we have lots of 3s on top and one more on bottom. So this, again, will simplify down and you just get 1/3. And so now my question is, does this right here converge or diverge? So that is, if you sum up 1/3 plus 1/3 plus 1/3 plus 1/3 forever and ever and ever and ever and ever, does it go to a finite number, converge, or does it go towards infinity, diverge? I guess anyone in chat or Anito, you can answer.
Oh, my bad. That's a great question. I feel like it'd go to infinity, but you're summing up a bunch of small numbers. So.
Yeah, it's slow, right? But
Yeah.
if you say that it goes to 1 million, right? Eventually, once I add so many terms to it, no, we're going to get bigger than 1 million, right? And
Yeah,
if you say
so
if it goes to 1 billion, well, we're going to get bigger than 1 billion eventually. So yes, this eventually, it is very slow, you're right, but it does surpass any finite number you say that it converges to, right? So.
Yeah, for sure. Thank you. Yeah.
Yeah, no problem. And so you would do the same sort of deal, plugging in 6, you would get something very similar. And again, then you kind of think about the series and whether it converges or diverges. In this case, formally what you're using here is like the nth term test. And because the nth term test, right, this is not 0, it's 1/3, we know that the series will diverge. And so it kind of, you have to think about some of your previous tests. So this is sometimes where, comparison tests or nth term tests for divergence, ratio tests, geometric series tests, things like that would be useful. All right, one more question here, and we'll double check and make sure that the Q&A is going well, and then do another question. Gabriel, you have the floor.
Yes. So I had a question just about it. It's about part A, but it's when you have to use the sigma notation to express the answer. So like, for example, like in this case, like f of x was equal to 1/x, so that can't really be represented by any of the I remember there's like the whole list of like all the sigma notations and all that.
Yes.
So we would use that let's just say this f of x was like represented by one of the ones in the list. We would just use that sigma notation and obviously modify whatever we have to. But
yes,
in this case, because it's not on the list, we have to use the f to the nth derivative times a over n factorial times x minus a to the nth power.
Yes, exactly. And I would probably just go on to say the fact that it's not represented on the list is very compelling, but also anytime that you have a different center. So for instance, even if I asked you about f of x equals 1/1 minus x, and I told you that it was centered about x equals 3, even though you have this on the list, right? It's the power series centered at 0. It doesn't give you the power series centered at 3. And so whenever you have a different center like this, you really have to rework the entire problem from scratch. So that list right there is only good when your center is 0. And those have a fancy name, right? Maclaurin series.
Oh, okay. I understand. Thank you.
Cool. Yeah, no problem. How's the Q&A going, Yuan?
Yeah, there's one left which is asking the x equal to 6, the endpoints.
Yes.
Can we use alternating series test?
Yes, you should be able to. Let's see. I'll give the speedy version of that. So this is going to be -1 to the n, 3 to the n divided by 3 to the n plus 1. That's after you plug in your 6. Oh, and no, it looks like lots of things are going to cancel here, unfortunately. Right, so you're going to have oh wait, -1 to the n here, and then divided by 3. Yeah, it's just regular old 3, right? Because you have one more on bottom than you do on top. And so this would be, if n was equal to 0, you would have 1/3. If n was equal to 1, you would have -1/3, and then 1/3, and then -1/3, right? Back and forth forever and ever and ever. So unfortunately, this does not, right? If you look at the piece that's not alternating, the limit doesn't go to 0. And so the alternating series test doesn't work here. This again will be an nth term test by divergence. So this will diverge. Because if you just look at the items on the list, right, they never tend towards 0. They just jump back and forth, 1/3, -1/3, forever and ever. Excellent. All right, well, let's take a look at what you voted for next. Let's see, that was 13. It looks like, oh, there's a 3-way tie right now. Looks like we're going to do example number 11. It's just the first one on that tie. So determine of this series here if it is convergent or divergent. And so, yeah, a lot of this is just kind of remembering chapter 11 and all those things that we used to do. And in particular, right, before the exam, I gave a review session and kind of we outlined when you're given a series like this, how do you know what to do? And so I would recommend going back and reviewing your notes, maybe even reviewing that video of just kind of a good outline of when you see a problem like this, how do you know what to do? And so in particular, I think everyone's favorite test, or at least historically, if we were to vote or whatnot, everyone loves the ratio test of all the tests, right? And so it's tempting to say, well, I'm going to try the ratio test on this. But I'm here to say, right, if you use the ratio test on this, you will get L equals 1. That is, the ratio test cannot determine. And so you'll spend a lot of time and you'll get nowhere, unfortunately. And so we need to realize that, right? What are the main indicators that tell us that the ratio test is going to fail? And in particular, it's the fact that we don't have any exponential functions and we don't have any factorials. If you see either one of those, the ratio test usually does a wonderful job on those. But the fact that we don't have any exponentials and no factorials means that the ratio test isn't probably going to do so well for us. And so then we have to think about, okay, what are some other tests that we could use? And in particular, the fact that we see roots and we see polynomials, this is something that usually the limit comparison test does quite well at. So yes, we are going to be using a comparison test. And of the comparison tests, right, my favorite is certainly the limit comparison test whenever it works out. But remember, we also talked about, right, when does the limit comparison test not work out? Well, this is usually when you have a natural log or a sine or a cosine, stuff like this. So it's just a generally good section to go back and review, kind of right before our exam on this material, right? We had a good review of kind of all the different tests and when you should be using which one. So we're going to use the limit comparison test here. Remember, for the limit comparison test, you need to kind of figure out something to compare with, right? That is, I need to figure out what is my b sub n going to be. And the way that we do this is that we go through each one of our factors and we try to determine what is the most important piece. And importance is really denoted with how large does it get as n goes to infinity. And so in particular, one factor is here in the numerator. We have an m versus a 3. And again, kind of eventually n is going to be going off to infinity. So if I can pick only one of these things, after all, we are trying to simplify things down. If I can pick only one of them, I think that the n is going to be much more powerful as n goes to infinity, right? It's going to get a lot larger than 3. And so I'm going to be picking the square root of n as my simplified down version that kind of captures the most important bits of this series. Now, the second factor here is down in the denominator, right? Factors are anything that are strung together with multiplication or division. And so we have this n squared plus 2n. And so again, I'm trying to simplify down. I'm going to try to pick only one of these things. And so I need to think about which is going to be more important as n goes to infinity, which is going to have the most kind of weight behind it. And I'm here to claim that, right, n squared will be more important. So n squared will be significantly larger in the long term. And in fact, even once you plug in like 1,000, let's just double check here, right? If you plug in 1,000 for n, we're going to have n squared is going to be 1,000 times 1,000. So that's going to be 1,000,000, right? We have 3 zeros and 3 zeros. And then if we plug in 1,000 for n, we're going to have plus 2,000. So 1,000,000 is way, way, way more than 2,000, right? If you gave me $2,000, I'll be mildly happy. If you gave me $1 million, that is significantly more. And so yes, n squared is considerably larger than 2 times n as you plug in larger and larger values. We only plugged in 1,000, but once you plug in even larger values, it really separates. So yeah, 2n. Mildly happy. Well, I don't know. Give me $2 stack. All right. Well, fair enough. I was filing my taxes and I paid so much, and I don't know, I get some money back and it's close to like $2,000. So I don't know, just $2,000 doesn't go as far as it used to. I agree with you guys that, you know, when I was a college student, $2,000 would make me ecstatic, but now it's like, all right, I can go buy some more landscaping blocks or build a fire pit or something like this. Anyway, back to math. So this is the thing that I think we should compare with. And by the way, if we're successful, I can then say very quickly, right, that this is going to be 1 divided by n to the 3/2, right? There's a little bit of canceling, just knowing that the square root of n is the same thing as the 1/2 power. And so things cancel very nicely. And this is going to be 1 over n to the 3/2. If I was to sum this up, 1 over n to the 3/2, this is going to converge by p series. And so the last thing for me to do is really to showcase that we've made a good comparison. I think we've done a decent job, but in order to showcase that their fates are actually tied together, we need to do that whole limit stuff, right? We need to do the limit as n goes to infinity of our a sub n's divided by our b sub n's. So let's go ahead and showcase that we've actually made a good comparison. So this is going to be the limit as n goes to infinity. And remember, this is on our formula sheet as well. And so I recommend that, of course, that you take a look at this. For instance, the ratio test, right? You're very sad if you get a limit of 1, right? For the ratio test, that's kind of like the worst outcome. That means that you haven't succeeded and you need to think about some other tests and all that sort of stuff. However, with the limit comparison test, if you got an answer of 1 out at the end of the day, remember that means that you made a great comparison choice, right? Any answer that's larger than 0 but not infinite means that you've made a good comparison. So let's go ahead. I'm going to divide by, or I'll multiply by the reciprocal here of this stuff here. So notice again, kind of, this is another case where not simplifying will actually be to our benefit here. So notice I didn't just divide by this 1 over n to the 3/2. I divide by our less simplified one. And that's going to help me out, especially, you know, thinking of this sort of like in terms of the ratio test and whatnot. I'm going to put together all of the like pieces. So for instance, I'm going to have the square root of n plus 3 and the square root of n. We're going to have n squared divided by n squared plus 2n. And as n gets very, very large, I think we're hopefully all still quick at this, and just to say that this is going to be 1, right? The fastest way is to say that these have the same power. And so it's going to be the ratio of the leading coefficients, 1 divided by 1. So that's the algebra way of figuring out horizontal asymptotes, what happens as you go off to infinity. We also had a calculus way. Calculus 1 would say that we're going to divide through by the highest power in the denominator. And so you could do it that way, or the calculus 2 way, you could do L'Hopital's rule to this. So whichever way you'd like to do, that's certainly fine. And either way, you're always going to get 1. For this first one here with the square roots, though, this one's a little bit more complicated, and I would recommend first rewriting it as one big old square root. And then we're going to use that property of limits that says that, hey, you can go ahead and push limits inside of continuous functions. And so if you can tell me what this limit is going to be, you can take that answer, throw it inside of a square root, and you win the game. So in particular here, well, this is again going to be just a rational function, polynomial divided by polynomial. They're the same degree and everything. And so it's just going to be the ratio of the leading coefficients, 1 divided by 1. We do have to throw that inside of a square root, which doesn't do a whole lot to 1, admittedly. But this right here would be our final answer. And so the last thing is always some, finalized statement, right? Because the answer isn't 1. The answer is that we've made a good comparison. And so whatever happens to our B sub n's also happens to our A sub n's, right? So since this here converges by the P series test, we know that our more complicated thing will also converge. 1 to infinity by the limit comparison test. All right, there we go. So yes, it converges by the limit comparison test, and you saw what we compared with. Let's take a few questions here. Riley, you have your hand up. What's going on?
I'm sorry, I meant to put it down. I understood what I was getting wrong.
Oh, okay, great. No problem. Anito, then you have the floor.
So since we know that our B sub n converges by the P series test, would we need to actually do the work for the limit comparison test in order to figure out that it will converge by the limit comparison test?
Yes, because you need to make sure that you've actually made a good comparison. So for instance, if I had made a mistake, for instance, and let's say I left the 3 here or something like that, a little bit silly, then this here converges by P series, right? You could just basically take out that root 3 and you basically have 1 over n squared. So this converges by P series. And yet when you do this here, you'll find that the limit doesn't go to, let's see, how do I have this set up? So yeah, it's not going to go towards any finite value. It's going to go off to infinity. And so this is saying that their fates are not actually tied together. What one does, the other doesn't care about at all, right? So even though your B sub n's converge, your A sub n's just don't care. And so that's the important bit here, is that you need to make sure that you've actually made a good comparison. And if you don't do that, then there's no reason to suggest that your A sub n's care about your B sub n's.
All right, for sure. Thank you.
Yeah, definitely. What's going on in the Q&A, Yuan?
Yeah, some questions about the final.
Okay.
Oh, maybe there's one asking this question. Could we also say that because Bn converges and it is bigger on the interval of the problem, then An converges?
So a question about, can you instead use the direct comparison test for this?
Yes.
I would say that it's not inherently obvious that B sub n is always greater than or equal to A sub n. Let me go ahead and put this back as it's supposed to be. The main thing, so when you divide by less, you do get a larger value. So the fact that we're trading out instead of n squared plus 2n for n squared, that would give you a larger result. However, deleting some bit off of your numerator is going to actually create a smaller result. And so that's why I say it's not clear that overall, will it be bigger or will it be smaller? Now, if this instead of +3 had been -3, for instance, then you could use the direct comparison test. We'd also have to start at a different starting value, right? It wouldn't make sense to plug in n equals 1. But that's why the direct comparison test is so, I don't know, it's definitely a lot less favorable in my eyes to the limit comparison test, because then you really have to care about all of your inequalities. And with the limit comparison test, you don't care if it's smaller or bigger, just so long as you've made that good comparison. And so, it wouldn't be fast to use the direct comparison test because again, getting rid of this 3, it's not clear if that's going to overall make larger or smaller values for your B sub n. It's not a slam dunk. How about that? Good. Any other questions?
So which one we would try first, limit or direct?
Limit comparison test. Limit comparison test. Unless if there's, and remember, so this came up in 11.4 is when we discussed all this. So if anyone wants to go back and do a little bit of review. But for the most part, I try to use the limit comparison test exclusively. There's only a handful of situations where kind of you really need to use the direct comparison test. In this class, it's typically if you're given like a natural log, then quite often the limit comparison test doesn't do so well with those. Or if you're given like a sine or a cosine, the limit comparison test doesn't traditionally do so well with those. And so if I see any of those, then maybe I'm thinking more on the order of a direct comparison test rather than a limit comparison test. Good. Arian, you have the floor.
Hi, I was just wondering if we do a limit comparison test or a direct comparison test, do we need to check for absolute divergence or, absolute convergence or conditionally convergent?
So it really comes down to the statement of the problem, right? In this case, it's just asking, is it convergent or divergent? And so since that's the bins that it wants us to decide, right? This series right here, does it belong in the convergent bin or the divergent bin? Then we don't care about absolutely versus conditionally. If it did come and say, classify this as either conditionally convergent, absolutely convergent, or divergent, then you would have to worry about breaking it down into absolute versus conditionally.
All right, thank you.
Yeah, definitely. Good. So with that, why don't we go ahead and peek at this? It looks like example 16 has come out in the lead quite considerably. So we'll take a look at example 16. Find the limit of this sequence here. And we have 1, 0, 2, diverges, or none of the above. So yes, this was an 11.1 style question. And remember, so the limit of the sequence, right? This is a little bit confusing at first. We needed to remember kind of what this phrase actually means. And for sequences, these are lists of numbers. And one of the main questions that we ask whenever we had a list of numbers is, does this list seem to be heading towards anything? So that is, as n goes to infinity, what's happening to the items on our list, right? So really, this is a limit problem. As you see, limit, but you don't see the limit as n goes to infinity. That you have to remember from our 11.1. So when it says the limit of the sequence, right, that means, well, the limit as n goes to infinity. So let's go ahead and plug in our specific thing here. And notice I'm going to go ahead and rewrite this. Instead of the nth root, I'm going to go ahead and raise that to the 1 over n power. Right, just like the square root is the 1/2 power, the cube root is the 1/3 power, same sort of deal here. The nth root is going to be the 1 over n power. Whenever you have powers raised to more powers, you can go ahead and multiply these results, right? So I'm going to go ahead and multiply these, and this is going to give me n to the 2 over n. And as n gets very, very large, both the base is changing and it's going off to infinity, and the exponent is changing and it's going to 2 divided by infinity, right? Which is going to get very, very close to 0. This right here is one of our indeterminate forms. When you take infinity and you raise it to the 0th power, it's not clear what will happen. Normally, infinity raised to any power, right? If you take a very large number and you raise it to first power, if you take infinity and you multiply it by another very, very large number, or if you take infinity, you raise it to the cube power, right? All of these are very, very large. But we also have another rule that says when you take anything and you raise it to the 0th power, right, it's always 1. And so we have these conflicting rules. Is it infinity? Is it 1? Is it something in between? It's indeterminate, right? So this is now leading us to 6.8, which was all about indeterminate stuff. And so really, even though this is in the context of a chapter 11 problem, the way that we're going to solve this is with L'Hopital's rule. And so we need to use L'Hopital's rule in order to solve this problem. And so in order to solve this, right, whenever you have a variable in both your base and your exponent, this is one of the key times where you want to apply a logarithm. So I'm going to go ahead and consider a different problem. And this made up problem that I'm doing here is one where we have a logarithm. If we know the answer to this, then we will be able to solve the other one just by applying an E. So with this, the main reason why we want a logarithm is because logarithms have this wonderful power rule. You can take your powers and you can bring them down just as coefficients. And let me go ahead and rewrite this here one last time. So this is going to be 2 times the natural log of n divided by n. And now as n goes to infinity, you're going to get, well, the natural log goes to infinity. And also the denominator, which is just a regular old n, is going to go off to infinity. So we're going to have infinity over infinity. And now the setup is perfect for L'Hopital's rule, right? We have it in this fraction form. We have the infinity over infinity situation. So according to L'Hopital's rule, this will still have the same limit as when you take the derivative on the top and on the bottom. So when I take the derivative on the top, when I take the derivative on the bottom. And now as n goes off to infinity, right, we're going to get 0. So dividing by 1 doesn't do a whole lot. You have 2 times 1 over n. N's getting very, very large, right? So you're going to have essentially 2 times 0 here, which is 0. My answer is not 0, by the way, right? This was a different problem. Mine was a made up problem that had a logarithm in it. However, right, from this, we know that, well, we just need to undo our logarithm in order to get the correct answer, right? So it's all right. Basically, you can apply a logarithm temporarily, so long as you don't forget about it. You need to undo the logarithm. And right, so our actual answer with our limits here is going to be e, right? Because that would cancel out with our logarithm to the, and our answer was 0. So this is going to be e to the 0th power, which is going to be 1. So our correct answer here is actually A, 1. All right, that was example 16. Let's see, no hands raised right now. Anything going on in the Q&A?
Yeah, there's a general question about, not this one, about the final.
Okay.
Do you have any suggestions on how to prepare for the exam, or is there some sort of study guide that has maybe 50 or 60 practice problems that display the types of the problems that could appear in the exam?
So yeah, a couple of different things that are coming to mind with that question. I would recommend, right, we made a practice exam in D2L. So I'd recommend that you take a look at that. Those have all of the questions kind of coded appropriately into the kind of the D2L formatting and everything. I would also make sure that you go back and review all of your previous exams and previous quizzes, right? Because again, those were questions, they're already coded in D2L. So it's very easy for us to take them from one place and put them in another place, first off. And that's not to say, right, you will certainly see new questions on the final exam as well. We are coding new questions and all that sort of stuff. But it's very possible, right, if we like those questions that we asked once already, right, that we still like them and we will ask them again. And so I would take a look at those and make sure to review all of your old exams and quizzes and make sure that you know how to do those problems if they were to come up again on the final exam. After that, I would probably start saying, you know, you should review some of your web work and maybe even, you know, the problems that we're going over in class, sort of deal. And worst comes to worst, right? Of course, the textbook has a lot of problems for every single section out there. So if you find a section that you really need more help with, you know, maybe after thinking about looking at this problem here, you say, man, I really need to go back and revisit L'Hopital's rule, right? And you go back to the quiz and the exam, you find the question about L'Hopital's rule and you say, I want even more practice, right? You go back to the web work, you do those. And the final step would be go to the textbook, right? And then you have all sorts of questions. So that's kind of the, maybe the order of operations, I would say, if you really want to delve into a particular topic. Good. Well, with that, it is 2:40, so that's probably where we're going to call it. Just want to remind you guys that I have office hours today from 4 until 5 o'clock, normal office hours. So come and hang out and we'll do some more math and talk about really anything that you'd like to talk about. And then again, on Friday, I have an extra review session. So if you're available during my, again, normal office hour time, 4 to 5 p.m., we're going to be holding it in this URL. Here on Friday, our normal class Zoom URL. That'll be our kind of last opportunity for some review session with me anyway. So, all right. Thanks again, everyone. We'll stick around as always for a few questions, and good luck studying. And if I don't see you between now and the final exam, good luck on the final, of course. All right.